Hello, everybody. Good morning. The topic of my presentation is Febuxostat loaded SNEDs for oral management of gout, a drug release-based study. The agenda of the presentation will be introduction and rationale, followed by objectives, methods and results, conclusion, and future prospects. Gout is one of the commonest form of attenuated rheumatological disorder. It is characterized by hyperuricemia, which leads to deposition of monosodium urate crystals. As per literature review, 20% of the purines comes from the diet, while 80% from the cell turnover and de novo synthesis of nucleic acids. Purines is metabolized to hypoxanthine and xanthin and further to uric acid in presence of xanthin oxidase enzymes. Uricase converts the uric acid to allantoin, which is water soluble and is excreted in urine. Some uric acid accumulates in the joints and leads to inflammation and further to gout. Febuxostat is a selective inhibitor of xanthin oxidase and hence decreases the uric acid levels in the body. Recent reports on incidence and prevalence of gout vary widely across the globe. The prevalence of gout increases with advancing age. As seen in the graph, prevalence is high in developed countries as compared to the developing ones. In recent years, there has been a complex association between gout, hyperuricemia, and comorbidities. The comorbidities associated with gout are hypertension, hyperlipidemia, chronic kidney disease, peripheral vascular disease, erectile dysfunction, obstructive sleep apnea, osteoporosis, and fracture. The rationale of the study is that febuxostat belongs to BCS class 2, having Tmax of 1 hour and oral bioavailability of 40 to 50%. The plasma half-life in adult is 5 to 8 hours with normal renal function. Approximately 80% of the oral dose is not observed and undergoes extensive hepatic metabolism. One of the most popular approach was to develop SNEDs. The various advantages of SNEDs are improvement in oral bioavailability, ease of manufacturing and scale, high stability, sterilizable, and not influenced by lipid digestion process. Also, it has been reported that SNEDs target the intestinal lymphatic system and are uptaken by chylomicrons. The drug, once reaching the intestinal lymph, gets into the systemic circulation via the junction of left internal jugular and the subclavian veins. This leads to avoidance of hepatic metabolism. To overcome the above disadvantages of febuxostat, SNEDs was developed. The objective of the study was to develop, optimize, and evaluate liquid and solid SNEDs of febuxostat, assess its in vitro release, and perform the stability studies as per ICH guidelines. The purity of febuxostat was determined by pre-formulation studies and drug excipient compatibility studies was done. Lambda max of the drug in methanol was determined and the method was validated. Solubility of febuxostat in various oils, surfactants, and co-surfactants was measured by dissolving excess amount of the drug in fixed amount of excipients. As seen from the graph, the high solubility of the drug was observed in Campul MCM and Cefsol. In case of surfactants, the drug exhibited good solubility in labrafil, tween 80, and labrasol. While among the co-surfactants, higher solubility was seen in PEG 400 and PEG 600. In preliminary study, tween 80 and labrasol was selected for further study, while among the co-surfactants, PEG 400 was selected. Using the water titration method, the pseudo-ternary diagram was constructed. The wider region of the pseudo-ternary diagram indicated self-nanoemulsification. Globule size increases with higher oil concentration and decreased S-mix concentration. Optimization was done by QBD approach. As seen from the contour plots that as the concentration of surfactant increases, particle size and emulsification time decreases and transmittance increases. As the concentration of oils and co-surfactants increases, particle size and emulsification time increases and transmittance decreases. Liquid Smiths was prepared by dispersing febuxostat in a mixture of Tween 80 and PEG 400 and gently mixed at room temperature for 10 minutes. Campule MCM was weighed and mixed with S-mix and sonicated for 20 minutes to form a yellow transparent emulsion. Liquid Smiths was evaluated for various parameters like dye-solubilization test, cloud point measurement, emulsification point, etc. Snets was then filled in size 00 hard gelatin capsules. In vitro dissolution studies was done in paddle apparatus in three mediums, namely 0.1 normal HCl, phosphate buffer 6.8, and 7.4. Graphs show that in all the three mediums, maximum drug release was from batch 8, which may be due to higher S-mix content. When batch 8 was compared with API and the marketed product, more than 75% of the drug was released in 60 minutes. In order to mimic the gastrointestinal environment in vitro, diffusion studies was done in all the three mediums and compared with API and marketed product. The results showed that the release profile of SNETs was comparable to that of the marketed product. Liquid SNETs have various disadvantages like incompatibility of components with capsule shells, precipitation of drug during fabrication, and storage at low temperature. There are various solid carriers like aerosol, avicell, magnesium stearate, microcrystalline cellulose, etc. Batch 8 was then absorbed on various hydrophilic and hydrophobic carriers. From the powder characteristic studies, aerosol 200 was found to be suitable carrier for febuxostat. In vitro dissolution studies showed that aerosol 200 did not interfere with dissolution of febuxostat from solid SNETs. At the end of the study, dissolution was more than 75% for both the formulations. Stability studies showed that both liquid and solid SNETs were stable at refrigerated conditions and as well as at room temperature. The conclusion that can be drawn from the study is that the release of febuxostat from liquid and solid SNETs did not demonstrate any significant difference. The drug release from SNETs was found to be pH independent. SNETs offer various advantages like ease of handling, easily scalable and sterilizable, patient compliance, improved bioavailability, cost-effective for the treatment of chronic disorders like gout. Solid SNETs preserve the solubility enhancement and in vitro dissolution of SNETs and is expected to eventually enhance the dissolution and bioavailability of drug in vivo. Thank you for listening.